So far in our journey through the world of mathematical modeling, we've looked at data sets that result in straightforward relationships like linear relationships. We've looked at data sets that are a little bit more interesting, I guess, that have required cubic functions to model them most accurately. What we've learned is that we need different types of functions to model different types of data sets. We're going to learn about a new type of function. We're going to learn about rational functions. Simply put, a rational function is a ratio of two polynomials. If you ever get lost, what you can focus on, the first 5 letters here, ratio. Rational functions are a ratio of two polynomials. You've seen tons and tons of polynomials. So, for example, one rational function could be 9x to the 5th minus 2x squared plus 9x plus 14 over x plus 1. It's a pretty exotic one. Another one could be 1 over x. In each of these cases, in both of these cases, the numerator and the denominator are both polynomials, so therefore f of x and g of x are both polynomials. So far with modeling, we've looked at taking data sets and turning them into nice models. What we're looking at with rational functions, we're going to take functions and turn them into graphs. And the nice thing is, and I know you're going to be super excited about this, is we're turning these functions into graphs by hand. I know, it's very exciting. We are going to follow a few steps, and it's going to seem like there's a lot of steps, and it's really not as bad as it seems. We're going to focus on the first 3 steps right now, and then later we're going to focus on the last 3 steps. First, we're going to analyze and try to work on the domain of the function. So let's say we had g of x is equal to 2x to the 4th minus x squared plus 1 over x squared minus 4. What's nice about rational functions is that we don't have to worry about rooting negative numbers and ending up in imaginary land. We won't have any roots in rational functions, so we don't even have to worry about this. What we do need to worry about is dividing by 0. We're looking for the set of all input values, so we're trying to find out which values result in dividing by 0 here. Meaning we're going to focus on the denominator. In this case, the denominator is x squared minus 4. We want to know when that is equal to 0 because we want to know when we would be dividing by 0. Luckily, this is a pretty easy thing to solve, either straightforward without factoring or with factoring. So we could either do it that way, or you could factor and turn it into x plus 2 times x minus 2 equals 0, which tells you that x is equal to 2 or negative 2. You should, either way, result in the same answer. This tells us that the domain of this function is x such that x cannot equal 2 or negative 2. So that's step 1. Find the domain. You're analyzing the denominator. Next, we're going to try to locate the intercepts. We're going to try to locate the intercepts. There are 2 types of intercepts. Y-intercepts, the y-intercept, if there is one, is when x is equal to 0. And the x-intercepts, there can be as many as you want, there can be many of them, when y is equal to 0. Generally speaking, the y-intercept is easier to find. Generally speaking. Let's take a look at our function right here. The y-intercept in this case would be when x is equal to 0. So if we actually look at g of 0 here, ended with 2 times 0 to the 4th minus 0 squared plus 1 over, not x, 0 minus 4, which is going to be, because all of these cancel out, 0, 0, 0, we're left with 1 over negative 4. So we now know the y-intercept is equal to 0, comma, negative 1/4. Can there be more than one y-intercept? No, because if there was more than one y-intercept, a vertical line would pass through the function more than once, the y-axis, and this rational function wouldn't be a function. We're dealing with functions. Y-intercept, pretty straightforward. The x-intercept, or intercepts in this case, can be a little bit trickier, and this is where we're going to spend a lot of our time in the coming days. To find the x-intercept, we're looking for when y is 0. To make a fraction equal 0, we need the numerator to equal 0, which means that we need to know when 2x to the 4th minus x squared plus 1 is equal to 0. You might say to yourself, I've never worked with polynomials of this degree, and you're probably right. We will be working with higher power polynomials. I will expect you to be able to work flawlessly with quadratics and linear functions. We'll be working with cubics, 4th degree, 5th degree, and maybe even higher than that. It gets pretty messy, but let's start off. Let's see where this leads. So we're trying to solve this. We would love to be able to factor. You should always be looking to factor, factor, factor. In this case, you're dealing with something that's actually a false quadratic. It almost looks like a quadratic. And this is not really the scientific term, but I like that term. I call it this because if you make a simple substitution, you can make it look like a quadratic. We're going to make x squared equal a. Could be any letter you want. If we then substitute into here, we end up with, well, you can first write it as 2x squared minus x squared plus 1 is equal to 0. Now, if x squared is equal to a, this becomes 2a squared minus a plus 1 equals 0. We're now dealing with a quadratic. You can tell me all about quadratics, and you'd hope this is factorable. You might try something like this. You're not sure. I'm not sure. Can we find something? I mean, you might think it's something like this, you know, plus 1, minus 1, but if you try that out, it doesn't really work. You end up with a minus 1. It's so close. Well, what we can check is we can find the discriminant. That's the b squared minus 4ac part of the quadratic formula. And in this case, it's going to be negative 1 squared minus 4 times 2a times c1. And that's going to be 1 minus 8, which is negative 7. Well, since b squared minus 4ac is less than 0, we know this has two imaginary solutions. So it means that this function can never equal 0 without a being imaginary, which means this function right here can never have a numerator equaling 0, which means the function itself can never equal 0. What does that mean? It means that g of x can never equal 0, so the function never crosses the x-axis. Now, this seems like it's not super important now, but it's one of the many pieces of information we're going to gather. So let's just pause for a second and take stock of what we know. We know that this function, we first found out that the domain is x such that x cannot equal 2 or negative 2. We found out that the y-intercept is 0, negative 1/4, and as for x-intercepts, there are none. We have no x-intercepts. We found out a pretty good amount so far about this function. If we keep on moving to step 3, you'll notice that we've done this before. We're going to test for symmetry. And we test for symmetry by throwing in negative x into the original function. So if we take this function right here and throw in negative x, what happens to the original function? We're going to test for symmetry on this function right here. So g of negative x, remember you can't just plug in one value, you have to plug in negative x, is going to equal 2 times negative x to the 4th minus negative x squared plus 1 all over negative x squared minus 4. We simplify this a little bit and we end up with 2x to the 4th minus x squared plus 1 all over x squared minus 4. Now what's happened here? Let's take a look. So now we know that g of negative x is equal to this, And what does that look like? Well, this is the same, this is the same. Well, it looks like nothing has changed. In fact, nothing has changed, so what does this equal? G of x. So what does that mean? We've shown that g of negative x is equal to g of x, so this function is even, which means it's symmetric over the y-axis. So those are the first 3 steps. You need to find the domain of the function, you need to find the intercepts, and you need to test for symmetry. We're going to remember that by saying we're going to dis. We're going to dis the function. Later, when we learn steps 4 through 6, we're going to come up with more letters, and maybe you'll come up with something better than dis in the letters that I come up. But for now, remember dis. Yeah.